So let's start with heat exchangers theory. So we are going to cover different types of heat exchangers first, such as the double pipe, the shell and tube, the plate, and the compact. That are main types of heat exchangers. And all of these you have in your textbook, because first we are going to focus on the different types of heat exchangers and how to solve heat exchangers. Once we learn how to solve heat exchangers, we are going to learn now how to design heat exchangers. Okay, so we are going to go step by step through heat exchangers. So what are heat exchangers? First of all, we need to go through the definition, and heat exchangers are devices that facilitate the heat transfer between two fluids at different temperature. And in the majority of the heat exchangers, the two fluids are not in direct contact. What are the main modes of heat transfer in a heat exchanger? Well, we have two main modes of heat transfer in a heat exchanger. The first one is convection, that occurs in the boundary layer of the fluids on each side of the solid wall. The second primary mode of heat transfer in a heat exchanger is conduction, that occurs in the wall itself. Typically, then, due to these modes of heat transfer, we construct heat exchangers of highly conductive materials, such as metals. Examples are aluminum, copper, stainless steel, or nickel alloys. That obviously, as you can see from the selection of metals, when using a nickel alloy, you will have finally a more expensive heat exchanger than using, for example, the stainless steel or aluminum. We have different types of heat exchangers for different applications, because different applications require different hardware and different configurations of heat transfer equipment. So the question would be what to choose, and that's what you are going to learn when we focus more towards design of heat exchangers, right? Because you need to design the heat exchanger for a particular application. The first type of heat exchanger that we are going to evaluate is the double pipe, and is the most simple type of heat exchanger. As the name says or implies, it's just a double pipe, okay? One small pipe inside a big pipe, and one fluid goes through the inner pipe, and the other ones go through the annular section that just covers the small pipe. So one fluid flows through the smaller pipe, while the other fluid flows to the annular space between the two pipes. And we can have two types of flow in a double pipe heat exchanger. We can have parallel flow, as you can see in this image, and it's clear by the arrows, that both cold and hot fluids enter the heat exchanger at the same end and move towards the same direction. We can have also counterflow, and it's more clear if you see this image and look at the arrows that shows the direction of the cold and hot fluids. So hot and cold fluids enter at opposite ends of the flow and flow in opposite directions, right? For example, cold in, right? And then cold out. Just follow the black arrows. Then the hot in, just follow the pink arrows, hot out. They are entering from opposite directions, right? The double pipe, as we already said, is the most simple way of heat exchanger or geometry of heat exchanger. But the most common one is the shell and tube heat exchanger. It's the most common heat exchanger in industrial applications. And it consists of a large number of tubes packed in a shell with their axis parallel to that shell. So as you can see here from these images, right? These are the tubes, right? And all of these that covers the tubes is the shell, right? And you have the different parts of the shell and tube heat exchanger here denoted in this image. So one of the fluids flows outside the tubes through the shell. Okay, so we have one fluid inside the tubes, the other fluid flowing through the shell. Okay, and typically we place baffles, like you can see, are denoted by these lines in this diagram. So baffles are commonly placed in the shell to force the shell side fluid to flow across the shell to enhance heat transfer and to maintain uniform space through the tubes. Okay, that's why they have this kind of constant spacing in between baffles, because not only help to direct the fluid through the shell, it also helps the baffles to keep the tubes in place, ordered. Okay, and well, shell and tube heat exchangers are relatively large in size and weight. And you have an image similar to this one in your textbook that shows all the different parts of the heat exchanger, of the shell and tube heat exchanger. The shell and tube heat exchangers can be further classified by the number of shells and tube passes involved. For example, this one that I have here to the left side of this slide is a one shell pass and two tube passes. Why? Because it has only one shell, right? And how many times the fluid passes through the shell? One, two. One shell, two tube passes. This would be a two shell for two passes. This is one shell, this is another shell, and how many passes? One, two, three, four. So it's two shell and for two passes. So whenever someone tells you, I don't know, two shells, eight passes, you know what it means, right? Or how the construction of a shell and tube heat exchanger happens. But typically, as you can see, these are the tubes. So this is a real image, a real size tube and heat exchanger. Okay. So as you can see, this is the baffle, right? And there are different baffle cuts, and we will see that later. And all of these ones are the tubes. So you can see how many tubes you can accommodate in that one. So there are thousands of tubes there, right? So, and here you have a person here, so you can see more or less the size of this shell and tube heat exchanger. Another type of heat exchanger is a plate and frame heat exchanger, and the name comes from the geometry, as you can see. It consists of a series of plates with corrugated flat flow passes. The hot and cold fluids flow in alternate passages. Each cold fluid stream is surrounded by two hot fluid streams, resulting in a very effective heat transfer. So as you can see, for example, here, this cold fluid is surrounded by two hot, right? The red ones in this image implies the hot fluid, and this one is the cold one. So well suited to liquid heat exchange applications. That's important. This type of heat exchangers, we use them typically for liquid to liquid heat exchange applications, provided that the hot and cold fluid streams are about the same pressure. So this is good for liquid to liquid applications. The compact heat exchanger, that is this another type of heat exchanger, has large heat transfer surface area per unit volume. And in this case, we have a variable that helps us to describe this type of heat exchangers, and is the area density, or beta. That is the heat transfer surface of a heat exchanger to the volume ratio. So typically, these compact heat exchangers had very high values of beta, larger than 700 meters squared per cubic meter. And just to give you an example of compact heat exchangers are car radiators, which have beta around 1,000, glass ceramic gas tube heat exchangers, the regenerator of a Stirling engine, and the human lung can be considered also a compact heat exchanger because of the beta value or area density. The compact heat exchanger, when to use it, we typically use it for gas to gas and gas to liquid or liquid to gas heat exchangers. And typically we have cross flow configuration. That means that two fluids move perpendicular to each other. But this cross flow can be further classified, and you have these two images to show the classification. We can have unmixed flow, so please focus in this image with the gray fins. So plate fins force the fluid to flow through a particular interfin spacing and prevent it from moving in the transverse direction. So that's why we have those gray fins that you see there to force one fluid through them and the other to the tubes. So that's why it's unmixed. Where areas we can have mixed flow configuration for compact heat exchangers in cross flow, like you can see in this image, where the fluid is free to move in the transverse direction because we don't have the fins, right? The fins are not there to direct the fluid. So we have here a mixed flow, okay? So we can have those two configurations for compact heat exchangers cross flow. So let's focus a little bit more towards shell and tube heat exchangers. Why? Because they are the most commonly used in industry, okay? So typically, a shell and tube heat exchangers consist of a shell, and we already say that it's nothing more than a large diameter pipe, typically in the range of 12 to 24 inches and larger, and also consists of tubes, ranging in number from 20 to thousands of tubes. One fluid is directed through the tubes and the other inside the shell, but outside the tubes, like you can see in here, right? And here again, you have all the parts: the shell, the tubes, the baffle, the inlet, the outlet, etc. We have tube dimensions of nominal sizes for our heat exchangers, okay? And for example, here I'm showing table 9.2, physical dimensions of condensate tubes in terms of BWG. And all of this you don't have in your textbook. All of this is in I sent you a chapter 12 with design notes. There you can find nominal sizes for heat exchangers. So these are typical dimensions of tubes in terms of BWG, Birmingham wire gauge, that indicates the wall thickness. Also, the wall thickness, well, it can be changed to inches or centimeters, okay, whatever needed. But if you see in design tables or more design tables or nominal sizes for tubes in heat exchangers, you will find this BWG. Why? Because most of the theory of heat exchangers was developed in England. So that's why you will find most of the nominal sizes also in English units, okay? Or BWG in case of the wall thickness. We can have different tube orientation, and we are going to talk more about that when we deal with the design of shell and tube heat exchangers. But here are some common orientations that you can find in practice: the square rotated, or triangular. This is how you arrange the tubes inside the shell, okay? And depends on the service your heat exchanger is given, okay? For example, for very for dirty services where you expect a lot of deposits, you will use preferably the square configurations. Why? Because it's easier to clean. You can pass currents of hot water, or you can just scrub through that big space. If you put a triangular one, is going to be more constricted. You can arrange more tubes in a triangular, but for cleaning is not suitable for dirty services. Okay, that is more towards clean services because just you need to give maintenance to your shell and tube heat exchangers, right? So depending on the service, one tube orientation is preferred over the other. Also, we'll deal with this table later when we are designing heat exchangers. And these tables help us to accommodate number of tubes depending on the number of tube passes that you have in here and the nominal size of the shell. Okay, so later on I will show you how to use this table, but this table you have it also in your notes for heat exchanger design. So this table helps us to accommodate in different geometries, like for example, 1 inch square pitch or 1/4 inch square pitch, the number of tubes depending on the number of passes you are designing, and you can select the appropriate nominal size of shell. And these tables go like, they're very long tables, and they might be included in your, I think they are in the chapter 12. Another important part of the shell and tube heat exchanger, because we are focusing right now on shell and tube heat exchanger, right, is the baffles. The baffles have three functions. The first function is to support the tube. Second, to maintain homogeneous the tube spacing, like we already mentioned it. And the third one, to direct the flow of the fluid in design pattern through the shell. And the baffle, we have different geometries for the baffle, right? So we can have different shapes for the baffles. And one important section or segment of the baffles is the baffle cut that at the end gives you the final geometry. And this segment called the baffle cut is cut away to permit the fluid to flow parallel to the tube axis as it flows from one baffle space to another. And again, you can have different baffle cuts, and that depends on the fluid and the service you are giving. Okay. In design of heat exchanger, something that you should not forget is that you will get what you designed for at the end. You will be the designer, and you will be choosing a lot of things, from the material to the cuts, the baffle cuts, the nominal sizes, the number of passes. So at the end, you will get what you designed for. Okay, so um, pressure drop is pretty important in design a shell and tube heat exchanger. The pressure drop is a major constraint in thermal design of shell and tube heat exchangers. A thermal design of a shell and tube heat exchanger is meaningful only if it is optimum and the extent of the optimal constraint by the pressure drop. Optimization of thermal design requires maximization of the overall heat transfer coefficient. Remember the one that we checked long ago, the U, the overall heat transfer coefficient, where we put all together all the resistances, the convective and conductive resistances. So that is your optimization or your optimum design, thermal design, depends on the maximization of this overall heat transfer coefficient or effective mean temperature difference, the logarithm temperature difference that we study when we study tube banks. Okay, that is the mean temperature difference. So as to minimize the heat transfer area subject to constraints, pressure drop may be a major one. So pressure drop is very important for this optimization. And overall heat transfer coefficients can be maximized by maximizing shell side and tube side flow velocities, which in turn is governed by the allowable pressure drop, as higher velocity means higher pressure drop, right? So this is a design equation or an equation to calculate the pressure drop in the tube side. And this equation is recommended by several authors. There are some other equations that you can find in different design books, but this is a good one that can help you to calculate the pressure drop in the tube side, where F is the friction factor, L is the tube length, MP is the number of tube passes, D is the diameter inside the tube, the inside diameter of the tube, rho is the fluid density, and B is the average fluid velocity in the tubes. So these equations, you have them in the textbook, chapter I sent to you. And we have similarly a pressure drop in the shell size. As you can see in the shell, things become more complicated from the equation you have in here. Why? Because you have the baffles, and the baffles will be redirecting the fluid, so you expect more turbulence and more changes in your fluid there. So you need to account for all those pressure drops. So delta PS is the shell side pressure drop. Fs is the friction factor for the shell that can be approximated with this equation. L is the tube length. ds is the shell inside diameter. Rho is the fluid density. Bs is the average fluid velocity in the tube. dE is the shell equivalent diameter or the hydraulic diameter for a shell, right? Because it's not a circular cross-sectional area, so we need to correct for that. And we have a special equation for this shell equivalent diameter in here, or this one, depending on the pitch. What is the pitch? The way you organize the tubes. I told you, you can organize them in a square rotator, or triangular. If you have a square pitch or a square rotated, this will be your equation. If you have triangular pitch, you will have this equation for the hydraulic diameter of the shell. ST is the tube pitch, how the tubes are arranged, right? Like I already explained, square rotated, or triangular. And DOT, outside diameter. If you see here, the surface area um, of the shell implies two equations. That implies two new variables: the clearance and the baffle spacing. So the clearance is defined as this distance, the distance in between the two outside diameter of the tubes, right? And the tube pitch, well, depends on the how the tubes are arranged, right? And here I have the square geometry, and here I have the triangular geometry. Okay. Um, so we will go through this again once we go through the design of heat exchangers. Now I'm give you a big picture of what is a shell and tube heat exchanger. Okay. Some heuristics and rules of thumb that you might need to have in mind when designing heat exchangers. And again, this you can find in your chapter 12 for heat exchangers. In the tube side, you must place, or typically you must place, the corrosive, fouling, scaling, and high pressure fluids. Why? Why do you think you have to put the corrosive fluids inside the tubes? Well, because if you have a leak, where is it going to go? To the shell. So it will be contained there. It's not going to come outside. So it will give you time to think about what to do or how to solve the situation. Okay. In the shell size, typically you want to place the viscous and condensing fluid. And typically a delta P of 10 pounds per square inch is accepted maximum for low pumping cost. So when you are calculating those delta P's with those equations that I showed you previously, 10 PSI might be the number you need to check for, don't having excessive pumping cost. Nozzle numbers, we need to evaluate nozzle numbers now for the shell and the tubes, okay? Like we have been doing. Why? Because we need to calculate heat transfers, right? Heat transfer rates. So on top, I'm showing the nozzle number for the shell side that is given by an empirical equation that has been verified on a number of commercial heat exchangers. So this equation has been already verified in several commercial heat exchangers, and it results a good approximation for the number, nozzle number in the shell, okay? So 0.36 times the Reynolds to 0.55 prime to the 1/3. In the case of the nozzle number for the tubes, we can use this nozzle number equation. And this nozzle number equation, remember, is one that we use a lot in internal convection. Is the 0.023 Reynolds to the 0.8 prime to the N, where N equals 0.4 when you are heating the fluid and N equals 0.3 when you are cooling the fluid, okay? So this is a common equation that we are carrying from our internal convection. So these two equations are something that we need to have handy. So now that we went through a briefly overview of heat exchangers, type of heat exchangers, and you already realized the complication of a shell and tube heat exchanger, let's now start slowly to see different important terms and numbers that we need to calculate for a heat exchanger. And the first one is the overall heat transfer coefficient, because we mentioned that is important and that is something we want to improve in a heat exchanger, right? And I'm going to include the fouling factor in the overall heat transfer coefficient. So let's evaluate then what is happening in a heat exchanger, right? So a heat exchanger typically involves two fluids flowing separately by a solid wall. And just imagine the most simple case, the double pipe, like you have here in this image. You have, for example, the hot fluid passing inside the tube and the cold fluid passing outside the tube, right? So how heat is going to heat transfer? From the hot fluid to the wall by convection, right? We have a fluid. Through the wall by conduction is a solid. From the wall to the cold fluid by convection, because we have again a fluid involved. So how many resistances our network is going to have? 3, right? 2 convective and 1 conductive. 1, 2, 3, right? So for a double pipe heat exchanger, the thermal resistance of the tube wall is given by this equation. And the total thermal resistance is first convective, conductive, and second convective. And we check that very early in this course when we evaluate the electrical analogy, right? When one fluid flows inside a circular tube and the other outside of it, we have two different areas, right? We have one inner area and one outer area, right? Because we have the thickness involved. So we combine all the thermal resistances and we went through this. So I'm just recalling this, right? We combine all the thermal resistances in one single term that we name the overall heat transfer coefficient, right? And we rewrite our heat transfer equation in terms of this overall heat transfer coefficient and in a similar way of Newton's cooling law, because heat transfer rate is the overall heat transfer coefficient times the area multiplied by delta T, that is our gradient of temperature, right? So we went through this equation. And we said that we can calculate the overall heat transfer coefficient based on the inside surface area of the inner pipe and based on the outside surface area of the inner pipe, right? And you already know these equations. We went through them. So I'm just recalling. So this overall heat transfer coefficient is so important for design of heat exchangers. And actually, there are tables that summarize typical values of the overall heat transfer coefficient. And you have this table in the notes I sent to you. It is table 12.1, typical overall heat transfer coefficient. And this is only one page of that table. The table extended for pages, okay? And why we have these tables of the overall heat transfer coefficient? Well, because this data can be used for preliminary sizing, for process evaluation, or trials values for design. And actually, because depending on the process I'm giving to you, you can come here and check more or less what is the range of the overall heat transfer coefficient you have to get, okay? Or use this value to start your iterations. That's the other thing. That's why these tables become so useful, okay? So again, someone calculate for you the overall heat transfer coefficient ranges, because as you can see, there are ranges, right? Like for example, heat exchangers, hot fluid water, cold fluid water, the range should be between 800 and 1500. So you have a range there to help you with preliminary sizing of heat exchangers for different services. And you know what is the overall heat transfer coefficient, right? There's no trouble with that. Good. However, in heat exchangers, we need to add an extra resistance to our heat exchangers, okay? Why? Because performance of heat exchangers usually deteriorate with time as a result of accumulation of deposits on heat transfer surface areas. So the layer of deposits represent an additional resistance to the heat transfers and cause the heat transfer in the heat exchanger to decrease. So we are adding an extra resistance because the more we use our heat exchanger, right, it's going to deteriorate, right? It's going to undergo or deposit or corrosion, right? So the surface area is going to change due to the use, okay? So the heat transfer, the rate of heat transfer can decrease. And we name all of these, the deposits, the corrosions, all those external effects that can impact your surface area for heat transfer. We name it the full-in factor. And that would be the RF, the extra resistance we need to add. So this full-in factor help us to add the net effect of these accumulations on heat transfer. And two common type of fouling is precipitation of solid deposits in a fluid on the heat transfer surface and corrosion and other chemical fouling. So as you can see, this is how it looks, a full surface area for a heat exchanger. You see how the area is affected? And this is after cleaning our heat transfer area, right? And again, this will look this is a full surface, right? It's all dirty. So the fouling resistance can be determined experimentally by 1 over the overall heat transfer coefficient dirty, or including the fouling resistances, minus 1 of the clean overall heat transfer coefficient, or the heat transfer coefficient without fouling, okay? So the overall heat transfer coefficient for a fuel heat exchanger is going to be U dirty equals 1 over the fouling resistance on the inside surface plus the fouling resistance of the outside surface plus 1 over the overall heat transfer coefficient for the clean surface. And where did you get this resistance for fouling, or this RF, right? Well, you get it from tables. We have tables for these resistances depending on the fluid or the fluid you are dealing with. For example, brackish water, ethylene glycol solutions, compressed air, cold gas, etc. And if you can see, some of them have two ranges of values. For example, brackish water has a range of fouling resistance between 0.004 and 0.005. So when you are solving, which value you should choose? Well, typically the best is to choose the worst scenario, right? Because that can give you a little more space in case your area got damaged faster than you think. Or so the best idea is always to design for the worst scenario, right? Let's solve this problem so you can see how to calculate the overall heat transfer coefficient with a dirty surface, okay? So remember, we're starting step by step. So the first step is the overall heat transfer coefficient. We have a long double pipe heat exchanger that is the most easy and more simple way of a heat exchanger. One small pipe inside a big pipe. So the cross section of which is shown in the figure below. So we have this double pipe heat exchanger here. And it consists of a 2-inch Schedule 40 steel pipe positionally concentrically within a 6-inch Schedule 40 steel pipe. So the 2-inch is inside the 6-inch. The inner pipe carries 30 Celsius brackish water at a mass flow rate of 16 kilograms per second. And 427 Celsius compressed air at 800 kilopascals flows in the annular space at a mass flow rate of 0.1 kilograms per second. So we have air here and brackish water in, right? Find the overall heat transfer coefficient for clean heat transfer areas or surfaces and full heat transfer surfaces. So clean and full, or clean and dirty, right? So we want to know those values, and we have given a lot of properties. So we are given already the properties of air at 700 Kelvin, the thermal conductivity, right, the brands, the viscosity, and also for the water, we have a lot of properties given, right? Like almost, I think all the properties we need for the water. Okay, so let's start solving then. And this is another diagram, right? Which shows all the resistances, but I'm sure you already realized about the resistances, right? So first, for the gas, for the air, we have to use ideal gas law to get the viscosity. The viscosity was not given. So I calculated with ideal gas law. Alternatively, you can look for it in tables. So using the ideal gas law and recognizing that the specific gas constant of air and the density of the air at 800 kilopascal and 7 kelvins is P over RT, right? And then the kinematic viscosity is the absolute viscosity divided by the density I calculated with ideal gas law. Why? Well, we need this to get the Reynolds, and with the Reynolds get the Nusselt. Why we need the Nusselt? Because we need to calculate all the convective heat transfer coefficients that are not given. So as you can see in this problem, we are getting the overall heat transfer coefficient from scratch, okay? So we need to get the Reynolds, the Nusselt, the convective heat transfer coefficients. Then once we have the convective heat transfer coefficients, put them in the overall heat transfer equation, right? So it's a very long problem, but at the same time, I think it helps you to visualize how to obtain an overall heat transfer coefficient from scratch. So let's follow then the methodology to solve this problem. So the inside and outside radius of a 2-inch Schedule 4 steel pipe, the nominal size, can be found from tables. So the inside radius of this 2-inch Schedule 4 steel pipe is 0.02625 meters, and the outside is 0.03015 meters. Now, the inside radius of the bigger pipe, the 6-inch Schedule 4 steel pipe, is 0.07705 meters. We are given the mass flow rate, so this is data from the example. For the water, we have a mass flow rate of 16 kilograms per second. For the air, 0.01 kilograms per second. To calculate the overall heat transfer value, we must first find the heat transfer coefficients for the two fluid streams. Then we need the Reynolds for the inner pipe. Remember, the water goes through the inner circular duct. So 4 times the mass flow rate of water, I'm using the Reynolds number for mass flow rate that I give you in your notes, divided by pi d, the diameter, multiplied by the viscosity. That gives us a Reynolds number of 4.8 10 to the 5. Now, we need to calculate the Reynolds number for the annular section where the air is passing, right? But that's not a circular cross-sectional area. So we need to get first an hydraulic diameter, right? It's an annular area. It's not circular. So the annulus is a non-circular duct. So we must find its hydraulic diameter. How we find it? 4 times the cross-sectional area divided by the wet perimeter. So it's what I have in here, and that is my hydraulic diameter. Then to calculate the Reynolds with the hydraulic diameter, I first need to get the mean velocity of the air in the annulus, right? Why? Because we need this value to calculate the Reynolds using the hydraulic diameter. So the mean velocity is the mass flow rate of air divided by the density of air that we calculated with ideal gas law, multiplied by the area, pi r3 squared minus r2 squared, right? Because that's the area where dictated by our annular space. So that velocity is 1.59 meters per second. Now we are ready to get the Reynolds for the annular space. Reynolds of the annular space, mean free velocity times hydraulic diameter divided by kinematic viscosity. Reynolds of 1.7 10 to the 4. So if you already realize, right, our two fluids, it was 4 10 to the 5, and this is 1.7 10 to the 4. Both are turbulent, right? There's no doubt about that. So now we can assume that we have fully developed turbulent flow and smooth ducts, right? So then we can use our Ditus-Boedler equation, right? That allows us to use Ditus-Boedler. So Ditus-Boedler is 0.023, Reynolds to the 0.8, Prandtl to the 0.4, because the water is heated by the air, right? So if I put then numbers, I get a Nusselt of 1602. Then the heat transfer coefficient for the inside surface of the 2-inch pipe is the nozzle times the thermal conductivity given or from tables divided by the diameter. Very careful here. The H, or convective transfer coefficient, is calculated with the diameter. And from tables, we have radius, and we have used radius so far. And I have seen this mistake, even if you found it trivial, I have seen this mistake a lot. You don't multiply by 2 the radius to put there the diameter. So that will give you a different H value. So that's why I put here 2 times radius 1, okay? So that gives me an H value, or convective heat transfer coefficient, for the inside surface of the 2-inch pipe of 1.8 × 10⁴. Now let's go to the other side. The air is cooled by the water, so the nozzle number is, instead of 0.4, is 0.3, right? Because in both sides we have turbulent, we assume fully turbulent and smooth pipes, so that's why we can use the Ditus-Boetler. So cool, and then we can get a nozzle of 51.1. And here I put a note on that, on the fluid heated and cooled, but you already know that. Hence the heat transfer coefficient in the annulus is 28.6. And here we are using the hydraulic diameter, right, to get the H, because it's a non-circular cross-sectional area, right? Noting that area I, or AI, the inner area, is 2 pi R1 L, and area out, or area node, equals 2 pi R2 L. The overall heat transfer coefficient based on the inside surface area is this equation. And here I just developed the areas, and I put in terms of radius only, so not a big deal. Let's K 64 for the steel pipe wall, right? Because we need this K value here for the steel pipe. And we have everything else. We already calculate HI and H naught, right? Is what we did in the previous slides. We put numbers into here, and we have an overall heat transfer coefficient based on the inner area of 32.8 watt-meter square Kelvin. But I want that you note something at this point. Check the resistances. That's why I put them one by one in the denominator. And check the convective resistance, this one that I put a lot of arrows there. If you see, the convective resistance of the air stream clearly dominates the overall heat transfer coefficient, right? These values are too small. So if the convective resistance of the water and the conductive resistance of the pipe wall are neglected, the U value is around 32.9. So as you can see, they are not having huge impact. It's this one that is dominating and giving us the latest value of the overall heat transfer coefficient. This gives you an idea of how important are the convective resistances, right? So you have to be very fine in your analysis of the convective heat transfer coefficients from internal and external convections from previous chapters, because those impact heavily your heat transfer coefficient, okay? Now, if we just add the fouling resistances for brackish water and compressed air from tables, so here I just read from the table, right? The resistances for brackish water, and I choose the worst scenario, the highest value. And then for compressed air, and I add those values here in my equation for U-dirty, right? So resistance in, out, fouling in, fouling out, 1 divided by clean, the clean that I got in here, gives me an overall heat transfer coefficient for a dirty surface of 32.1. So if we compare the 32.8 for a clean surface versus the 32.1, sorry, for a full or dirty surface, the overall heat transfer coefficient is 2.1% lower for the dirty heat exchanger, right? So this results in a 2.1 reduction in heat transfer. And so on. If you keep working with that heat exchanger and keep adding fouling resistance, right, it will be the time where your heat transfer is going to reduce to the time you need to give cleaning or service to that heat exchanger to come back to a good heat transfer rate. So as you can see, is highly demanding in time to get the overall heat transfer coefficient for a heat exchanger, right? Especially starting from scratch, from the H values for convection. That's why I need that you gain a lot of practice during for this exam too, right? Because that's knowledge that we will be carrying to heat exchangers for sure. Okay, Travels, questions?